Dear friends, Maths Aspirants is a collective of mathematics students, research scholars and faculty members across India, initiated by myself in 2017, and we used to organize several online problem solving session series to help the students who prepare for different national level competitive examinations. As a part of that ongoing series, today we have a special session focusing on the forthcoming CMI ISI entrances. Today we blessed to have Mr. Lalit Thuwal, a research scholar from Indian Institute of Science, Bangalore, with us to handle a session focusing on these exams. So he will discuss problems from previous year question papers of CMI as well as ISI exams. Today and tomorrow we will have this session. So the second part of this session will be on tomorrow, and the time may be in the afternoon. I will inform you the right time in our groups. Possibly it will be around 2 p.m. in afternoon. So I welcome everyone to this problem solving session, and I wish all the participants this time will be very helpful in your preparations, the final round preparations for these exams. And I would like to express my sincere gratitude to Mr. Lalit for accepting our invitation. Once again, I welcome everyone to this program. Welcome, Lalit.
Thank you, Professor, for the kind introduction and for giving me the opportunity to speak before such a distinguished audience and truly motivated group of students preparing for advanced mathematics and competitive exams. I'm truly honored to be here. So before we begin today's session, where I will be discussing problems from the CMI 2018 entrance exam, I would like to take just a moment to share a valuable resource that could be significantly enhance your preparation all. So I'm going to present my screen. Let me know if you can see it. So if one of you can confirm. So yeah, is it visible?
Yeah, yes.
Yeah, so yeah, okay. So this is a YouTube channel of Mathematics where you can freely access complete solutions of different exams. You can see here in the homepage, CMI solutions, ISI solutions, CSR net solutions, and NBHM solutions, GATE solutions, and TFR solutions, and more. Okay, so these solutions are organized systematically and complete solutions. Okay, for example, CSR net solution, if you click there, you will get all the playlist, and these are complete solution. You can access them freely and enhance your preparation. So, okay, so let me present the screen of my iPad. So let me know if you can see that. And I believe that you had a chance to practice all these problems before coming to the session, because I had asked Professor to share this in the group. So, okay, feel free to ask questions. Okay. So let me start with the first question. What it says, let G be a group of order 6 and C1, C2 dot 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 Ck with the distinct conjugacy classes of G. Which of the following sequences of integers are possible values of this tuple? Okay, so basically this question is asking about the class equation of a group of order 6. Which of the following can be the class equation? So we know the class equation of a group is, we know that order of G is equal to order of ZG plus G does not belongs to so, right? So I want to point out here that each term appearing in the class equation, either an index of the normalizer of some specific element or it belongs to the center. Okay. So whenever some element is in the center, then its class is, I mean, suppose that A is in the center, right? Then its conjugate is A only, none other elements, because it commutes with every element. So you can write it like this. and you get A. So the only conjugate to A is A. Okay, so the class equation of a group will look like this. So 1 plus 1 as many times the order of the center of group. Okay, times and plus dot dot dot. So these terms are indexes of the normalizer of the some element. So each term here will divide the order of group. Okay, so now let's go by option by option. So the first one says that all elements are self-conjugate. I mean, all the elements are in center. Okay, so if we pick G equal to this cyclic group of order 6, then G is equal to center of G because it is abelian, right? So each element is conjugate to itself only. So in this case, we get the class equation as 1, 1. So the first one is possible, right? This is possible. And the second one, B, it is not possible because it says that the class equation will look like this, right? 1 plus 5. But what I told you that each term in the class equation is an index of the normalizer of some element which is not in the center. So it means that the 5 should divide 6, but this is not true, right? 5 does not divide 6. Okay. So the order of each conjugacy class divides the order of group. Okay, because it's the index of normalizer of some element. So this one C. Now, but it does not mean that if 3 divides the 6, it will appear as a term in the class equation. Okay, this is not, this need not true. So can the class equation look like this? 6 equal to 3 plus 3. No, it is not possible because it says that the center of G in this case 3, right? But this is not possible for any group of order 6, but this is not possible for any group of order 6. Okay, let me show how. So if G is of order 6, then G is either S3 or Z modulo 6Z. Okay, up to isomorphism, the order of group, this group of order 6 is either S3 or Z modulo 6Z. So in this case, you have already seen that the class equation is 1, 1, 1, 1. And but what is the class equation of S3? Okay, C and D. I think we will discuss C and D together. So let me write C and D. So the class equation of S3 is this, right? Identity and the 2 length cycles and 1, 2, 3 and 1, 3, 2. So there is a fact that 2 elements in Sn are conjugate if and only if 2 elements of Sn are conjugate if and only if they are of same cycle type. Of cycle type. So what do I mean? They are of same cycle type means that when you write them as a product of disjoint cycles, then it is same. Okay, the cyclic decomposition is same. decomposition type. So in this, the conjugacy classes are the conjugacy class of I. So let me denote the class of I by this. So it is identity only because it is in the center. The class of 1, 2, it is all 2 cycles. Okay. And the class of 1, 3, 2, it consists of all 3 cycles. So the class equation look like 6 plus 6 equal to 1 plus 2 plus 3. Okay, so it means the D is possible, but the C is not possible. Okay, and one thing that suppose you have a non-abelian group, I mean, without this calculation, you can also infer that this is the only possible class equation of a non-abelian group of order 6. Why? Because see, first of all, you should know that class equation cannot be like this, right? 1, 1 plus, because otherwise this will be abelian. So, and if a group of order PQ is non-abelian when P and Q are primes, then its center is identity. Okay, so there will be one element. Now, 2 and 3 are only possibility. Okay, because 2 and 3 divide 6. So here will be divisors of 6. So 2 and 3 are only possibility. No other possibility will work. Okay. Right. So any questions in this? Ria, do you want to ask something?
Sir, order of ZG not equal to 3. ZG equals to 5.
Where?
Option C, D.
So no, I said that if this is the class equation, then this implies that order of ZG is 3, right? Oh, sorry.
We denote order of
Yeah.
ZG
Oh,
1
okay.
plus 1 plus.
Okay. Thank you. This actually does not implies. So this is completely wrong. I mean, this is not possible, right? So at least, yeah, thank you. So at least one should appear once, right? Because class of identity is always A. Yeah, thank you. So I don't need to do this now. Okay. So I mean, this is wrong because one is nowhere here. Okay. Yeah. Thank you. Any questions?
सर अपने हिस्ट्री के जब एलिमेंट लिखा 1 to 2 बार लिख 1 3 हो गया
अच्छा कोई नहीं, चलो वो तुम लोग करेक्ट कर सकते हो। ठीक है वो, हाँ 1 3 होगा वो, सही। अच्छा यहाँ भी 2 बार लिख दिया, ठीक है, राइट। और कोई कुछ पूछना चाहते हो? और we move to the next one. Okay, so this is question number 2. What it says, let R is f2x, choose the correct statements from below. R has uncountably many maximal ideals. Okay, so R is given to be polynomial ring over the field with 2 elements, right? So here I will use a theorem which you can prove, and I will let you know that how you can prove that. So theorem, F is a field, then Fx is PID. Okay, so let me ask you a question. What about the converse? How many of you can answer this question? If Fx is PID, where F is a commutative ring with unity, so must F be a field? Raise your hand if you can answer that. Just raise your hand. I would like to know. So the converse of this, that Fx is PID, then F must F be a field. Okay, so think about it. Okay, so how do you prove it? Let me tell you that pick any ideal of this fx and there exists a f in I such that if it is non-zero ideal, okay, so non-zero, such that degree of f is minimal. Why this is possible? Because why this is possible? Well ordering principle, okay? Every non-empty subset of natural numbers has least upper bound. You know that, right? Because if you will collect, I mean, consider the set of degrees of all the polynomials in I, then it is a non-empty subset of the natural number. So it must have a least upper bound. So, and that f is, I claim that that f is the generator of I. You can prove that, okay? It's the same. I mean, it's not difficult. So this is a PID. Now, the next thing is that f2x is countable, right? Countable or not? The polynomial ring over a countable ring is always countable, right? Because it is something like, so how do you prove that it is countable, by the way? You prove like this, okay? Degree I over f2, right? So I can write f2x as f2, the polynomials of degree 1, the polynomials of degree 2, dot, 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 right? This union is okay. So where AI is set of polynomials of degree I over f2, and can you see that AI is equivalent to this? Not actually this, but this is countable, right? You can show that this is similar to a subset of this f2 cross dot, 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 I, right? I times. I mean, you can take in place of I set of polynomials up to degree I, okay? If you will take up to degree I, then in this case, AI is equivalent to this directly. I mean, it is enough to consider this also. Degree up to I. Okay, so this ring is countable. Now, and each ideal in f2x generated by a single element, right? So we have at most countable ideals. Right? It means the A is not correct. Now, every maximal ideal of R has infinitely many ideals. Every maximal ideal. So another theorem about PIDs is that a maximal ideal maximal ideal in a PID generated by, can you complete this? Generated by ...
Irreducible element.
Okay. So irreducible element, right? Irreducible elements of F2X are not 0 and 1. Okay. I mean to say they are not constant because this is 0 and this is a unit, right? So a irreducible polynomial must be of degree greater than equal to 1, right? So pick a arbitrary ideal, maximal ideal, say let F2X be a maximal ideal, then there exists a irreducible polynomial F of degree say n such that I is generated by this polynomial, right? Because F2X is a PID, so every ideal will be generated by some element because it is maximal, so it must be irreducible element. Now what it says that, oh, it says that every maximal ideal has infinitely many elements, right? So this ideal look like Fx into Gx, where Gx is in F2X, right? So clearly this is infinite, right? It hardly needs comment to explain. Clearly it is infinite. So you understand, right? It is an infinite set. Why? Because say that its degree is n, right? So pick an element of degree 1 from F2X, right? Okay. If you want to understand, pick F1, F2 ... of degree 1, 2, 3 ... respectively. Now, then F1F, F2F ... these are of degree. F2X is an integral domain, okay? Are of degree n, right? N plus 1, sorry. N plus 1, n plus 2, n plus 3. So they are different degree polynomials. So they are distinct pairwise, right? So these are infinitely many elements which are here in this set. It means that each maximal ideal has infinitely many elements. So this option is also correct. Okay. For all maximal ideals, M of R is a finite field. Okay. So everyone knows that if we quotient by a maximal ideal, then we get a field, right? So now it will be finite or not. So pick a maximal ideal. So this is again generated by a polynomial of degree n, right? A polynomial of degree n. Polynomial of degree n. Say degree n say. So this quotient looks like this. A0 plus A1x dot 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 an minus 1 x to the power n minus 1 plus, right, where ai is in F2. Is it clear? Or not? Why? Can any of you let me know that why this is so? Raise your hand. Because see, if you pick, say you have a coset, right? Every I mean, this F2x is also a Euclidean domain. So by Euclidean algorithm, or I mean by division algorithm, you can always write gx as fx into hx plus rx, right? By dividing fx. And the degree of r here is either 0 or degree of r is less than degree of f, right? So this comes out to be rx, this coset, because this is a multiple of f, so it will absorb it. So we get this, okay? And the degree of rx can be either it is 0 or it can be up to n minus. So the quotient will look like this, right? And this is clearly finite because A0, A1, An minus 1 all have finitely many choices because two choices, each have two choices, right? So what is the order of this? Order of this?
2 to the power n.
Okay, 2 to the power n, right? So finite. If you quotient by a maximal ideal, you will get a finite field. So this is also true. Now the last one, for every integer n, every ideal of R has only finitely many elements of degree less than or equal to n. Okay, so this says that this is also EG. Okay, why this is EG? Because see, F2x has exactly 2 to the power, I mean, say, how many elements are there of degree 1? How many polynomials are there of degree 1? Degree 1 polynomial will look like this, right? 4. Right? So F2x has exactly 2 to the power n plus 1 polynomials of degree n, right? So it has finitely many elements of degree less than or equal to n. Okay, let me write it k, okay? For a given degree k, right? So you understand this? For example, say the number of polynomials of degree less than or equal to oh, actually, I'm wrong here, right? Less than or equal to k. This will be less than or equal to k. It was, I mean, okay. So exactly 2 to the power n plus 1 polynomials of degree less than or equal to 1. Okay, so any ideal of f2x has only finitely many polynomials of degree less than n equal to n, right? Any questions in this? Everything is clear? Okay, so let me go to the next one. So this from topology. Which of the following spaces are connected? So A, xy belongs to R square such that xy equal to 1 as a subspace of R square. So the graph of this looks like this, right? So you can clearly see that this is disconnected. Okay, not connected. And if you want to write a separation, so say the given set is A, then you can write it. Assume that this set is A. Okay, so you can write it x 1 by x is greater than 0 union. This is a separation of this. X is less than 0. Okay, so this is disconnected. Okay, the B, the set of upper triangular matrices as subspace of n, M and R. So let me take n equal to 3, okay, to make it clear. So for simplicity, take n equal to 2. In this case, your set of upper triangular matrices, say it is U, let us denote it by U. It looks like this, right? ABC comes from R. So if we define a map from R cube, so define R cube to U by which will send this tuple ABC to here. A, B, 0, C. So this map is continuous, right? Is continuous and homeomorphic rather, right? This map is continuous, and let me denote it by phi, okay? So phi of R cube is connected, which is U exactly, right? So it's connected because the image of a connected set under a continuous map is connected. So it means this is a connected. So now we have taken n equal to 2. Suppose that now take arbitrary n, right? So what you will define? You will define a map from R in general. Can anyone of you let me know that in general what will you do? Not from R cube. From where? R to the power?
n into n plus 1 by 2.
Okay. From this to U. Okay. So what will be the map? Let us denote the entries like this. Okay. A12, A1n, A21, A22, dot. Last entry would be no, like not like that. I mean A23, like this. Do you understand it?
So I think A22 will be there.
A22 will be there, obviously. Thank you. A23 and so on. And the next will start from A33, okay? And you will end at A N, N. Okay, this will go to A11, A12, dot, 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 A1, A22, dot, dot, dot. The last one is AN. And this is a homeomorphism, okay? Connected continuous map. So now everything is same as this one, okay? So this will be connected. Now, what about this one? The set of invertible diagonal matrices as a subspace of M and R. Okay, this is the set of invertible diagonal matrices. Okay, so see, there are few techniques to show that something is connected or not connected. How do you show that? Sometimes you define a map, say, assuming that X is connected, and you see that its image not comes out to be connected. That proves that the topological space is not connected. Okay. And if you want to prove something is connected, you define a map from some topological connected topological space to X, which is onto. That shows that your topological space is connected. These are techniques in the topology, you know, right? So see, for the C, we define this map. Let D be the, suppose D be the set of all invertible diagonal matrices. Okay, so phi with the determinant map. Okay, D to R. Which sends. Oh, by the way, do we consider? Okay, is it okay? So D to R, which sends each A to. It's a determinant, and this is a continuous map, right? A continuous map. I hope you know that. So what is the image of D? Phi of D would be? Can you find the image? What it would be? Okay, let me know.
R minus 0.
Okay, R minus G. So why that? Let me tell you. Okay. So because the matrices are invertible, so determinant is never going to vanish, right? So 0 will never be in the image. 0 will never be in the image. And suppose this matrix, say like this dot 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 1 goes to R, right? Under phi for any real number R. Suppose you have a real number R which is non-zero, then you can consider this diagonal invertible matrix. It is mapped to R under the determinant. So it means that D surjects here, right? So the image of D is this, but this is disconnected. This is not connected, right? Because it has a separation, you know that. It is disconnected. What does that mean? That means that so D cannot be connected. If it were, then the image under any continuous map should be continuous. Okay. So D is not connected. Now let me leave the fourth one as an exercise and let me tell you that this is connected or not. So yeah, this is not connected. So this is connected. Okay. This is same like this. So you will do it. Okay. So what does this represent? Do you know? In 3 dimensions. But you have to take the z greater than equal to 0. Okay. So you have to take only upper side. So now you can, I mean, see that which region, what we have to show less than and equal to 0, right? Yeah. So now, I mean, check yourself which region this represents. Okay. It is this or the complement of this. Okay. I mean, in any case, that is connected, but just figure out yourself. Any questions? Okay.
I mean,
So
it is visually clear why it should be connected.
yeah. Yeah. Yes. So any questions?
So, sir.
Huh? Okay. So let A be a n cross n nilpotent matrix. So A is written twice. Okay. We have defined a matrix e to the power a in plus a square by 2 factorial. Do you know that why this is well defined? You must ask yourself that why this is well defined.
The A is nilpotent, so this series will terminate after n
Yeah.
terms.
Okay, this is a finite sum, right? Yeah. Good. So solution. Choose the correct statements from below. First of all, A is nilpotent. So there exists a K. Yeah, we can say that. So A to the power n equal to 0, right? Where n is the order of the matrix. Okay. So every nilpotent matrix satisfies this because the characteristic polynomial of nilpotent matrix is x to the power n. Only 0 can be the eigenvalue of a nilpotent matrix. Can be not. I mean, it is okay. So इसलिए e to the power a is I plus a square by 2 factorial. Okay, let me write it like this. Dot a to the power n minus 1. Okay. Okay, so let me ask you a question. You can prove that. Okay, let me give it as a homework. A matrix is invertible if and only if all of its eigenvalues are non-zero. Okay, do it are non-zero. So, okay, one question I want to ask that how many of you know if I will discuss then A, if F is a polynomial, say where the matrix is Rx, okay, and A is a matrix in M and R, say lambda is an eigenvalue of A, then F lambda is an eigenvalue of Fa. And I know that all of you know this. So now the question is this, that all eigenvalues of Fa appears like this. Okay, that can you do that? Okay. I mean, that's not direct. Okay. I mean, it is very direct that because you will suppose that Ax equal to lambda x, then you will, I mean, with manipulations, you get this. Right. So f lambda is an eigenvalue whenever lambda is an eigenvalue. That what is the question? That suppose this happens mu y for some non-zero vector, mu is a scalar, then mu appears something like this. Okay. For some eigenvalue lambda. So, okay. Try it. Okay. I mean, this is true, but try to prove it. F lambda. Okay. So eigenvalues of for TA are what? See, all eigenvalues of a square dot 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 any power of k are 0. Okay. So of e to the power ta are 1 dot 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 1, right? Is it clear or not? Because if you put t here, you will get t, right? Ta. A is nilpotent, Ta is also nilpotent. Okay. So see, e to the power ta is this I plus ta, but that doesn't matter. Okay. This is a nilpotent matrix. Nilpotent matrix. Okay. Why? Because A is nilpotent, all its powers nilpotent, and all those powers commute among themselves. So their sum is also nilpotent. Okay. So the eigenvalues of this matrix are 0. That's why the eigenvalues of e to the power ta are this. So it is invertible. इसलिए determinant e to the power ta is 1. So it's invertible. Okay. This is true. Now, there exists a basis of Rn such that e to the power a is upper triangular. Okay. Is it true or not? Yes. Because similar to every matrix is similar to its Jordan canonical form, right? Jordan canonical form. Yeah, by the way, I want to ask. So it is diagonalizable or not? Why it is diagonalizable? Many of you say yes. Why? I have written 1, 1, 1 on the diagonal doesn't mean that these entries are non-zero. Okay. These entries are 0. Why this will be diagonalizable? Okay. So it does not matter whether or not it is diagonalizable, but the Jordan canonical form is a upper triangular matrix, right? Upper triangular matrix, Jordan canonical form. Canonical form. So B is true. Okay, there exists a basis such that this is similar to this. So it's a Jordan canonical form, and Jordan canonical form is always upper triangular. You know that. And this one, there exists a B such that A to the power A is similar to B, but the trace of B is 0. But the similar matrices has same trace, okay? Note that similar matrices have same trace. So trace of, if that is true, P e to the power P inverse is equal to trace of EA. What is the trace of EA? Sum of the eigenvalues. Okay. So that is n. If you will add all the eigenvalues, you will get n. Okay, because all the eigenvalues are 1. That cannot be the trace of B, which is 0. Right? It means cannot be equal to B for any invertible matrix P. Okay. So CH not true. What about the last one? There exists a basis of Rn such that A is lower triangular. So anyone want to answer this question? I will give you an interesting homework here, okay? So that A is similar to its always. Try this problem, okay? I hope that now you can see that D is true, right? D is true or not? Because see, e to the power A is similar to this matrix, Jordan canonical form, and you take its a transpose, you get a lower triangular matrix, right? And every matrix is similar to its transpose, okay? And it's a good exercise. Try this one. So let me write it true just, okay? So I have explained. So let us move to the next one. Okay, so are there any questions by the way? Okay. So yeah. So let me not discuss this one also, because this is just calculative, okay? You just have to find the partial derivatives and then take the dot product. Okay, there are calculations, nothing more than that. So I hope you will try this one. And if you are not able to solve it, then just let me know tomorrow. Okay, I will solve it for you. So this one is from Galois theory and the interesting one. So let's start. Okay, so let me give you a homework. I mean classwork first, not homework. So the number of real roots of 2x cube minus 3x square plus 6. So try it. How many real roots this equation has? Let me give you 2 minutes, okay, to decide it. Are you trying, by the way? Just react. Okay. So okay, do it and let me know how many real roots are there of this polynomial. This will required, okay, in the solution of this question. And here you will learn something very interesting in this question, okay? there is at least one real root, right? So are other two roots complex, non-real, or they are also real? Okay, so you can try that at home. Let me tell you, there is exactly one real root and the other two roots are non-real complex. Okay, and let me proceed. So you can just try intermediate value property and other things to decide that the roots will be non-real complex. Other two roots. Okay, there must be one real root. Okay, that is necessity. So A. There exists a subfield of C such that which is not a subfield of R, which is not in R, but F is isomorphic to this. Okay, first, this polynomial is reducible or irreducible? H.
It's reducible in Rx.
Okay, what about Q? This will reduce in R. 𝕒𝕒𝕒𝕒𝕒𝕒, irreducible.
Yes, sir.
Why?
Also, we can try rational root theorem, I think.
Okay, that can be tried. And okay, and 𝕒𝕒𝕒𝕒𝕒, other.
Sir,
What other?
Einstein criteria.
Right, that could be easy, right? Einstein criteria. So so what is the prime we are going to use? So take P equal to what prime?
3.
3, right? See, 3 divides 6, 3 divides minus 3, 3 does not divides 2, and 3 square does not divide 6. Okay, so it is irreducible over Q. If it is irreducible over Q, then so this 2x, the ideal generated by this irreducible polynomial, is a field, right? This is a field and isomorphic to what? Q. Attach a root of this, okay, where alpha is any root of 2. Okay, so take a complex root. So if we take a non-real root of 2 this ... Okay, then Q alpha is a field which is not inside R, and we get and Q alpha is isomorphic to this. I should have denoted this by something F, right? Because I had to write this often. Okay, anyway, so the first one is true, right? Any questions in the first one? Okay, the second one says that for every irreducible polynomial, cubic polynomial, fx is in qx, there exists a subfield f of c such that f is not a subfield of R, but f is isomorphic to this. So now I want to ask a question to you, that can you find a polynomial question? Okay, so let me write a question here. Question: can you find a polynomial f in over Q of degree 3 with all its roots irrational. It is possible or not? Just let me know. What do you think? Try to answer, okay? Otherwise, I feel that all are got disconnected. Is it possible or not? Or it is impossible? Oh, not it's a polynomial, irreducible polynomial. Okay, so that must be irreducible, by the way, because no root is there. Yeah, I mean it is enough to write polynomial just okay. That will automatically be irreducible if you will find. So, what is your guess?
My guess is no, because the sum of these roots have to be rational, then the product have to be rational, because
Yeah.
they are going to be the coefficients of the polynomial, right?
Right. Okay, then there may be 3 irrational numbers whose sum is rational, right? This is possible. And the
Yes,
product
the
is
product also has to be rational, and the product means taken two at a time, like AB plus BC plus CA.
that
That
has to
also
be.
has to be a rational.
Yeah, so but that might not, I mean, be a problem. Why do you
So
think
are
that
there
that would be a
three,
problem?
okay, so are there three rational numbers which satisfy this condition? That are there three rational numbers A, B, and C, such
mean-
that A plus B plus C,
Okay.
ABC, and AB plus BC plus CA are rational?
So yeah, there. So that's what I'm asking to all of you, that are there. This would not be an answer. This would be just one step further. Okay. So what is your guess, guys? That that would not be
Sir,
possible?
may
Huh?
sir, may I try?
Bolo.
I also think it will not be possible
Okay.
because when you have an irrational root of a rational polynomial, it is usually in some kind of
Okay.
pair. So it's not just
Okay.
x minus
Okay,
root
so
2
let me
alone.
tell you the answer. Okay. Actually, so I should know we have time constraints. So answer is yes, there is. Okay. And in fact, for each natural number n, you can find such a polynomial whose all roots are irrational. Okay. I will show you how can you do that. Not explicitly every time you can do that, but I will show you the existence. So how many of you have read about the Galois theory? Are familiar to Galois theory? Galois extensions. No one? Many of you have MSc, right? Studying in the MSc or passed out. Okay. Fine. So let me show you how. Okay. See. By the way, it is not difficult to construct such a polynomial. Okay. What you have to do, you have to see. Let me give you a hint. Not, I should not give you a hint. I think that, oh, you can see. You have to make a polynomial of degree 3. We in the integers. Okay, try to do this, which is irreducible over Q and which has at least 2 real roots. Then all the roots will be real, right? And no rational root that you can do. It is enough to verify that it has no integer roots. Okay. I mean, I have written this. This might not work. I'm just letting you know that what would be the procedure for that. You have to find a polynomial of degree 3 in the integers, which has no integer root, but all its roots are real. Then that polynomial will have all roots irrational. Okay. You have to verify that at least 2 real roots are there. So I mean, this is not that polynomial. Okay, this might not be that polynomial what I have written here. So okay, let me tell you that why that exists. Okay, so now the question that for every irreducible cubic polynomial, fx. Okay, so b. I'm letting you this solution because this will teach you something good. Okay, I mean, you will see now. Okay, so see, take zeta 7. This is 7th root of unity. A to the power 2 pi I by 7. We know that Q, when we attach zeta 7, the Galois group of this is a Galois extension. Okay, so the Galois group of this is isomorphic to, let me know, the Galois group of this Q zeta 7 is this. Okay, it is just this thing. Okay, and yeah, so this is isomorphic to Z modulo 6Z. You know that. So let me say denote the Q zeta 7, the seventh cyclotomic polynomial by K. Okay, and the group by G. So G has a subgroup of index 3. Yes or no? That is clear, right? Because G is isomorphic to this. So it has a subgroup of index 3. This implies, say, H. Okay. Fixed field of H. Fixed field of H. Say L. Has degree is Galois over Q. Why? Because Because it is normal. Every subgroup of G is normal. So the extension is normal. The fixed field is normal over Q and already separable because K is separable, right? So it's any sub-extension. H is normal subgroup of G and G is abelian. Any subgroup of abelian group is normal. Okay. So L is a 3-degree Galois extension. Galois extension. Okay. For some alpha. Because every extension of a field of characteristic 0 is simple. Okay. Primitive element theorem. Every finite separable extension is simple. So for some alpha C. Now say F is irreducible polynomial of alpha. Nomial of alpha. Okay. Say F is this. X cube ax square plus bx plus c. So now I ask you a question, why all roots of f are irrational? Can you tell me? So I'm saying that this Q alpha is totally real field. Okay. Why? Okay. So it has at least f. I think I need to add a page. At least fh, at least one real root, right? है ना? One real root. Say alpha bolo. Q alpha is L. Okay. Why? Because see, this is a normal extension. So normal extension. So all its conjugates will be there. Conjugates is in, say मैं beta बोल देता हूँ उसे. So beta, all its conjugates in Q beta. Okay. So L is nothing but Q beta. And it's totally real. Okay. Because if you are attaching a real root to Q, then you get a totally real subfield. Okay. Totally real extension. Totally real. Totally real. So all conjugates of beta are real. It means all its roots are real, but they cannot be rational because it is an irreducible polynomial. So all are irrational. Okay. Now one thing is that, so it means it's true. It's not true. Okay. In general, that for every irreducible cubic polynomial, so there exist cubic polynomials with all irrational roots, which are irreducible over Q. Okay. In fact, by this method, why I told you this, by this method, because this can be done just finding a irreducible polynomial over Q of degree 3, right? And you are done. But this, I mean, from this you learn something that from using cyclotomic subfields, you can always find a polynomial, a subfield of degree n over Q, okay, which is totally real. So the polynomial of irreducible polynomial of alpha has all its roots irrational. Okay. You can try to solve this, that this problem, this require, I mean, this will use exercise for each n there exists a Galois totally real field of degree n of extension of Q. Okay. You can try something similar. Okay. Just generalize it. So you will get answer here. You can replace 3 by n. Okay. Any questions? And others are easy. Okay. This one is very obvious because you can just take a real root. Okay. Let me solve it here. Take a real root of alpha, root of 2x cubed dot dot dot, then Q alpha is isomorphic to Qx dot dot dot. Okay. And for every D says for every irreducible cubic polynomial fx, there exists a subfield f of R such that this happens. This is also true, right? Why? Because let me write it here also. Okay. Copy. Yeah. Take alpha real root of fx in C. That exists, right? Because cubic polynomial means a polynomial of odd degree. So it means Q alpha is isomorphic to, in that case, Qx over this. And we are done. So we have solved all the questions, all the options. Are there questions? Okay. So let's move to the next one. For a continuous function f, define a and f equal to this sequence. This is integrable function, okay, because it is continuous over 0, 1. Choose the correct statements from below. So all the options can be answered just by observing that a and f, what is the mod of a? Just find that whether or not this sequence converts, okay? So try to find that. The mod of this sequence is 0, 1, x to the power n, fx, right, dx. So this is less than or equal to m x to the power n dx, where the supremum exists, right? Because f is a continuous function over closed interval 0, 1, so it is bounded. You must have read about it. So this we get. So it means if we solve it further, then we get what? What do we get? This, right? Okay. So, and this tends to 0. H and tends to infinity. So it means A and F is a convergent sequence. Okay. H convergent sequence for each F, continuous F, I mean, belongs to C 0, 1. Okay. This denotes the collection of all continuous functions over 0, 1. So, and each convergent sequence is bounded, right? Sequence is bounded and Cauchy, you know that. So the first one says the sequence A and F is bounded for every continuous function f because it is convergent, so bounded. And this option B says the sequence A and F is Cauchy for every continuous function. Yeah, obviously, because it is convergent, so it is Cauchy. The sequence A and F converts to 0 for every continuous function. That is what we have proved. And there exists a continuous function f. This is wrong because it says that the sequence A and F is divergent, but we have already proved that for each f it is convergent, so it is wrong. Okay. So this is very easy question, right? Any questions? Now the question number 8, it is from complex. Let f c to c be a holomorphic function. Choose the correct statements from below. Okay. Okay, A and B. How to solve that? Take f equal to fz equal to z, right? In this case, fz bar is z bar, not holomorphic, right? And fz equal to z is holomorphic, not holomorphic, and fr is also inside R, right? And it is exactly R, by the way, right? R mapped to R, right? Under this function. So, but R is not open. Everyone knows R is not open in C. Oh, by the way, it asks FR is open in R. So what do you think? It is open or not? So we have to take the another example. Huh? Okay, thank you. So fz equal to 1 works. Okay. In that case, FR is not open. So it is wrong. C. E to the power FZ is composition of two holomorphic maps. Two holomorphic maps, right? So composition of two holomorphic map is composition of two differentiable maps is differentiable, right? E and FZ are everywhere differentiable. So their composition is everywhere differentiable. So it means E to the power FZ is everywhere differentiable. Okay. That is what learn in when you start differentiability etc, right? Composition of two differentiable maps is differentiable. So E to the power FZ is holomorphic. Suppose that it says that FC is inside R, then FH closed. What does this imply, by the way? The image of a holomorphic map is inside R. So what does that mean? Can any one of you let me know?
Constant.
Sabas. F must be constant, right? The image of F is not dense. FH not dense. I will tell you why. Okay, not dense in C. Try this exercise. Okay, F C to C holomorphic. Non-constant map so that FC is dense in C. Dense means that every open set of C will intersect this. And this can be done just using Liouville's theorem. Okay, you don't have to go so far. Don't use Picard theorem and etc. Just try to do it directly, just using Liouville's theorem. Okay. So think that if it is not dense, do it by contradiction. Then there is some open set which will not intersect this one. Okay. Then you should think. Okay. Dense in C. So F must be constant. FZ equal to C for some C. C for every Z in C. Okay. Sum. FH closed in C for every closed subset. So it is true, right? Because singleton is always closed. So this one is also done. This one. This is very interesting. Okay. Let me do the first 10th. Okay. Then we will do that one. Solution. Let A be a non-zero 4 cross 4 complex matrix such that A square equal to 0. What is the largest possible rank of A? So see. Okay, there is an inequality for every A n cross n. Suppose if you have a matrix A, we know that. Do you know that? Let me know. Then we have rank of A. If A be there, rank of B minus n, rank of AB, and it is like this. Do you know this inequality? This is called something I'm forgetting that. Okay, no need to remember that, by the way. So if we put, so take A equal to B, okay, then we get rank of 2 times rank of A in case of 4, n equal to 4. So rank of A square, but rank of A square given to be 0 because A square is a 0 matrix. This means rank of A is less than equal to 2, but this does not mean that this is the largest possible rank. Okay. This does not mean that this is the largest possible rank, because this just says that the rank must be less than equal to 2. So we must produce an example. So what is the example? Just, you can take a Jordan canonical form of such A. So that would be like this. Okay, you can verify it. Okay, easy, right? So it satisfies everything. Okay, because this is the Jordan canonical form. If you don't take A to be 0, okay, because the 0 matrix will also satisfy, its rank is 2. So I mean, there are examples also whose rank is 2. So answer is 2. Okay, so keep that in mind. Sometimes we make a mistake because this might possible that by some way we get this right. Then we cannot say that the rank must be less than the largest possible rank of A is 3 unless we produce an example. Okay, so this is now let's discuss the last question. Okay, so what it says, let f R2 R be a twice differentiable function such that it vanishes at every number of the form 1 by n, where n is a natural number. Choose the correct statement. Solution. So it asks that what should be f0. F is continuous, right? Continuous. 1 by n sequence converts to 0. So f1 by n converts to f0, right? But f1 by n is 0 sequence. 0 constant sequence. So f1 by n converts to 0. But the limits are unique of a convergent sequence, right? Limits are unique. Limit is unique, I should say. Limit is unique of a convergent sequence. Convergent sequence. So f0 must be 0, right? It means the first one is true. Okay. And we want to find what f-0 will be. F-0, and this is also easy. Okay, if you want to find f-0, there are two ways to find f-0. So you can directly find like this: limit h tends to 0, fh minus f0, which is 0. You know that h minus 0. Okay, so we just need to find this limit. Okay, now we have given that f is twice differentiable function, so it means that this limit exists. Okay, and if limit exists, it does not matter which path you choose to approach 0, right? Because any you can approach 0 along any sequence, you will get every time the same answer. So pick this limit is equal to n tending to infinity f1 by n into n, right? And this is again a 0 sequence because this is vanishing every time, right? So this is 0. I mean, make sure that you understand everything. Okay, convince yourself. My h and n looking same. Okay, so let me make it. So any questions there? Are there any questions? No.
No.
Okay, thank you. So thank you for letting me know. So now what about f-0? So twice differentiable function. Now here you have to, I mean, do something. Okay, so see. Now you don't get something from here unless you use this, what I'm letting you know. See, there exists a sequence xn such that xn converts to 0 and fxn, this is my claim, and you fxn is 0 for each n. So how many of you can see this? This is true. This is my claim. There exists a sequence xn which converts to 0 and, oh sorry, not f, because this is given, right? So I will say F double dash, I will say. No, F dash, I will say F dash. Yeah, I think, yeah, I require this. Only 2 of you can see this. Okay, 3. Okay, Abhilipsa, why do you get such a sequence?
Sir, by Lagrange's mean value theorem, we can take.
Okay, fine. Good. So you have this, right? See, 0, 1, 1 by 2, 1 by 3. So by Rolle's theorem, you get by repeatedly applying Rolle's theorem. Okay, Rolle's theorem. Okay, we get xn satisfying this. Okay, and the derivative will vanish at xn, right? You can apply the Rolle's theorem now, or Lagrange's theorem. Okay, so from sandwich lemma implies that limit of xn is 0, right? Yes or no? And each xn is non-zero. Okay, now find f double dash 0. So if you want to find f double dash 0, for that what you have to do, limit h tends to 0, f dash h, and we know that f dash 0 is 0, so no need to put that here because we have already proved that h, and we know that this limit exists. Okay, so you can go approach 0 along any sequence because we have given that f r to r is a twice differentiable function. So this limit exists. So I will go along the path xn. Okay, so this comes out to be now. Oh, sorry, my h and n looks same. So sorry for this confusion. And n tending to infinity. Now it is n. Okay, xn over xn. So this is again 0, right? Because this sequence is 0 and xn is always non-zero C, right? I mean, this is defined everywhere. Okay, so it means f double dash is also 0, right? F is a non-zero polynomial. So how do you discard D? It is a non-zero polynomial. I mean, this is not possible. Right? F is a non-zero polynomial. Can F be a polynomial? Please answer it. I mean, if you answer, I feel that you are listening very carefully and you are following. So can F be a polynomial?
No,
Why?
because it has infinitely many roots, 1 by n.
Right. Because a polynomial has finitely many roots, no? No. Because a polynomial has finitely many roots, right? Yeah. So are there any questions? This is interesting one, right? Not the difficult. And you all know, I think, this theory. So yeah, I will wrap up. If you have any question, then please do ask. Okay. And I will send this PDF also. Okay. And we'll also send you the PDF for tomorrow's session. And it will be 2 to 3:30, right, sir?
Yes, we can arrange it on 2 to 3:30.
Okay, so it will be at 2 to 3:30, and I will send you the problems to practice. before
Yeah,
the
yeah,
session.
we can share it in the group.
Yeah, okay.
Okay, thank you, Lalit, for this nice session with a good collection of problems and with nice explanations.
Thanks.
Now the participants, if you have anything to share like feedback or any questions or any queries regarding ISI or CMI exams, you may ask now.
Hello, sir.
Yeah.
I'm Gayatri. I'm doing MSc from NIT Calicut.
Okay.
More time to process all the concept, but still when you write each and every sentences, it was easy to understand. Thank you so much for your valuable time. And thank you, Vinod sir, for arranging this kind of classes. Thank you.
Okay, thank you, Gayatri. Okay, any others? Yes.
Yes, sir, I am 𝕨𝕚𝕥𝕙 from Kasganj, UP. I am preparing for IIT JAM and CMI also. I want to ask some preparation tips and some books. Galois theory is a new concept for me. So can you suggest some books and notes also?
Okay, so you want to know about the books to read Galois theory or other books?
Other also and Galois theory also, because Galois theory is new for me.
Okay. So for Galois theory, you can read Patrick and Morandi book, Dummett and Putte book. And let me refer you a video, okay, where I have explained all the books of analysis, algebra, and I will send it. Okay, so I will share it, okay? Sir will share it to the group. Where I have, this is a detailed video where I have shared recommended many of the books. So for Galois theory, there are books you can write now also. Patrick and Morandi book and Dummett and Putte and Algebra by Arte. Okay.
Yes, sir. Thanks, sir. Thank you, Vinod, sir.
Okay, thank you, Dharmendra. Any others? If you have any feedback or anything to ask, you can make it now. Okay, Lalit, thank you.
Okay.
I'll just wind up here. So tomorrow